Hi, ladies and gentlemen, this is Mr. Green, and we're approaching the end of the semester, and I just wanted to get these last few lessons in here about geometry. Geometry. Yay, geometry. So what are we talking about? We're taking up some special issues in geometry. Don't forget, get your quiz corrections in. Make certain you got everything done before you, and no zeros out there in the grade book. We don't want to have zeros hanging around out there. We're looking at topological equivalence. Topological equivalence. This is a very, very, very major topic that when you get into this in college, you start looking at it from a really, really, really strange set of perspectives. Now, topologically, what are we talking about? We're talking about a flat surface with two holes in it. I just boiled it down to its basic form. This is also a flat object with two holes in it. This is also a flat object with two holes in it. This is also a flat object with two holes in it. All four of these objects would be considered topologically the same. That doesn't mean they're equivalent in any way, shape, or form. It just means the topology of them, the way they're put together, would be similar. Okay? This one over here only has one hole in it. Not the same. This one, I've got two objects. And I've got two objects up here. So these two could be considered topologically similar or equivalent objects. Now this one down here, this one's really, really, really strange. I've actually got two objects. I've got an object on the outside and an object on the inside. Okay? But that torus in the middle with that makes it a three-dimensional object. It doesn't really fit with any one of the other objects at all. Okay? This is topology. It's difficult. It's something that you have to visually look at it and examine it and see if you can't understand it. Okay? Along with this, you've been doing this since you were a little kid. You didn't know that you were doing it because they didn't talk about topologically equivalent objects, but they did talk about something that came out of topology, and that is a Jordan curve. A Jordan curve is a very simple closed curve divides the plane into two distinct regions, the inside and the outside. Inside, outside. So where did you see this before? When you did things like this. Determine which points are on the inside or the outside of the maze. Now to do this, I'm going to actually use a highlighter. And I'm going to try to be very careful with my highlighter. I didn't get it there. There it is. There's my highlighter. So out here is yellow. So I'm going to try to keep this yellow right here on the outside. See how this is outside? Everything else has been inside, is inside of that triangle, that object. See how it's closed over here? So that's the inside portion of it. And I went in the opening and I'm staying on the outside of the triangle. So this little maze is I'm coloring in the outside portion of it. E is on the outside of the triangle. But C is on the inside of the triangle. See how I'm going around here? I'm trying to be very careful with it. A is on the inside of the triangle. D is on the inside of the triangle. But B is on the outside of the triangle. So this point right here in the very, very middle of that object is in the outside of the triangle. Okay? You guys see how I got that? This point right here being outside of the triangle. I just stayed on the outside of the triangle. I didn't go on the inside at all. I never crossed a line, did I? That's the way you find out inside outside on triangles. This Jordan curve is very complex. This maze is very complex. But this is the way Jordan curves work. Okay? And it's all stemming from topology. Okay? Topology comes into play. Finding how to get water to all three of the houses in the neighborhood. Well, water was easy. Now, how do we get the gas to all three of the houses in the neighborhood? Well, I got to go to the gas here, and I'm going to go here to get to the house over here. Okay, and then I'm going to go over here to get to this one. And then get the electricity to all three houses. Wow, this is going to be difficult. If I got to go to the electricity to get to the houses, I'm going to go to this one. And I'm going to use that same thing. I'm going to go to this one. How am I going to get to house 3? Scratching his head, Mr. Green goes, I don't know how I get to house 3. Does anyone see how I could get to house 3? You know, there is a way of doing it. I think. Okay, so watch what I'm going to do here. I'm going to delete that line right there. Okay, I haven't got my gas going to house 3 yet, but I'm going to take my gas all the way around. All the way around. Like this. To get to here, to house 3. Now, my electrical line still coming around this way. I can come off of this and go right into the house there for electricity. So all three houses have electricity, all three houses have gas, and all three houses have water now. That's a situation of topology. That's the way this type of thing, this type of problems that you would be looking at in topology look like. Okay? This, Euler, you've seen a lot of different things that Euler has done in the past. Euler's formula is for any complex polyhedron. You can calculate the number of vertexes, the number of edges, and the number of faces. It is a simple little equation. The vertexes minus the edges plus the faces will always equal the number 2. How did he get this? It was a topology type of a formula that he worked through to get this to work. Okay? So looking at this one, how many faces are on this particular thing? Well, on faces, I see 6 of them. Okay? How many vertexes do you see on this one? I found 8 vertexes. And how many edges are there on this one? Well, there are 4 on bottom, 4 on top, and 4 between them. There are 12 edges. So let's look at our formula here. V minus E. Okay? 8 minus 12 plus faces plus 6. Okay? Well, 8 minus 12 is minus 4 plus 6 is 2. 8 minus 12 is minus 4 plus 6 is 2. We got 2. 8 minus 12 plus 6 is equal to 2. That's the way you can use that formula to figure out how many edges, how many faces, how many vertexes there are given a polyhedron. Okay? That's a cute little formula. It all came out of topology. Now, if you look at this, it's called a Mobius strip. That's where you take a strip of paper, you twist it once and put it together, and it makes a continuous, non-ending strip. It never ends, as opposed to just a cylinder where you tape the edges flat together without the twist in it. It would be a strip going all the way around. You can tell the difference if you draw a line on the outside of the strip, okay, and you keep going around and round and round, and you connect back to the line, and there was no line on the inside, then you know you have a cylinder. If you do the same thing with a Mobius strip, you go around and round and round and round and round and round, and the line, when it finally connects back together, would be both on the inside and on the outside of the strip. That is a continuous strip, and it never ends. Okay? So, using those type of things, you can draw lines to connect each topological figure with a rectangle that it represents. If my lines do this, they go up and then they go down like that. Oh, easier to do this one. This one here, where the lines are both going in the same direction, this one is going to be the cylinder right here. Okay? If I have two lines going this way and two lines going that way, this one is going to be the MOBA strip. This one, this one is going to be the torus. This one is going to be the MOBA strip, and this one is going to be the Klein bottle. This, taking a piece of paper and folding it this way, is a difficult process, but it is one that is a part of the topological concept of geometry. Okay? As you can tell, not one of my favorite topics, not one that I'm going to spend a whole lot of time on or put a lot of weight on, but if you have questions about it, please come see me in tutoring and we'll talk about it. Okay? I appreciate you guys telling me that you're in geometry. It does help. It really does. You just don't know. And I will talk to you